Picture the Earth. 1 meter from it, 1 single meter, place the Sun. At that scale, where would the nearest star be? Not across the room, not across the street. 270 kilometers away. That is the true scale of interstellar space. Our closest neighbor, the star system called Alpha Centauri, sits 424 light-years from Earth. That number sounds almost gentle. It is not. A light-year is the distance light travels in a full year. Light moves at 299,792 kilometers per second. In a year, it covers roughly 9.46 trillion kilometers. Multiply that by 424 and you get a number with 13 zeros, approximately 40 trillion kilometers. We have no intuition for this. Our minds are built for horizons, for days' journeys, for the scale of human life. The cosmos operates on a fundamentally different register. We know this because we have already tried. In 1977, NASA launched the Voyager probes, the fastest machines humanity has ever built. They travel at around 17 kilometers per second. That is over 60,000 kilometers per hour. Faster than any bullet, faster than any jet, faster than almost anything humans have ever made move. If Voyager 1 had been pointed at Proxima Centauri, the nearest member of the Alpha Centauri system, it would arrive in approximately 75,000 years. 75,000 years. The entirety of recorded human history spans roughly 5,000 years. The last ice age ended 12,000 years ago. 75,000 years ago, our ancestors shared the planet with Neanderthals. A mission launched today would reach its destination in a future so remote that the civilization that built it, the language it spoke, the technology it used, all of it would be ancient mythology to anyone waiting on the other end. This is the weight of those words. 70,000 years of darkness. Not darkness as metaphor. Darkness as a physical reality, the literal absence of sunlight in the void between stars, a void so vast it swallows civilizations whole. Before we can understand why reaching Alpha Centauri is nearly impossible, we must understand what it actually is, because the destination is stranger than most people realize. Alpha Centauri is not a single star. It is 3. At the heart of the system, 2 suns orbit each other in a slow gravitational waltz. They are designated Alpha Centauri A and Alpha Centauri B, and together they constitute one of the most beautiful and complex stellar environments we know of. Alpha Centauri A is the dominant partner. In many ways, it is a twin of our own Sun, a G-type star with a similar color and temperature. But it is slightly larger, about 10% more massive, and its nuclear furnace burns a little hotter. The result, it shines with roughly 150% the luminosity of our Sun. It is also slightly older at approximately 485 billion years, meaning it has had more time to forge whatever worlds orbit it. Its companion, Alpha Centauri B, is smaller and cooler, a K-type star with a warm orange tint. It burns at only half the Sun's brightness, but what it lacks in power it makes up in longevity. Stars like Alpha Centauri B can burn steadily for 15 to 30 billion years, far outlasting our own Sun's expected lifespan of 10 billion years. These 2 stars orbit each other over a period of about 80 years, a timescale that is almost poignantly human. A single person with a long life could, in principle, watch one complete revolution of this binary system. But their orbit is not a neat circle. It is an elongated ellipse. At their closest, a point called periastron, the 2 stars are separated by roughly 11 astronomical units, similar to the distance between our Sun and Saturn. At their farthest, apostron, they pull apart to 36 astronomical units, nearly the distance between our Sun and Pluto. Imagine standing on a planet orbiting Alpha Centauri A. Your primary Sun burns yellow-white overhead, familiar. But in the sky, there is a second Sun, a brilliant orange beacon thousands of times brighter than a full moon, casting its own distinct shadows across the landscape. As the decades pass, that second Sun slowly brightens, grows, and then, 40 years later, fades and retreats. Your world has 2 clocks, the 24-hour rotation of your planet and the 80-year heartbeat of the binary pair. Some nights both suns are on the same side of the sky, and there is no true darkness. Other nights, both set together, and the stars appear with a clarity that no human has ever witnessed from Earth. For centuries, Alpha Centauri was believed to be a simple binary. Then in 1915, astronomer Robert Innes, working at the Union Observatory in South Africa, noticed something unusual while examining photographic plates of the region. There was a faint star, invisible to the naked eye, moving across the sky at almost exactly the same rate as the Alpha Centauri pair. This shared motion, what astronomers call proper motion, was a strong clue. The star was not a distant background object. It was physically associated with the system. Parallax measurements confirmed it. This dim red ember was actually closer to Earth than A and B, sitting at 424 light-years compared to the pair's 437. Innes named it Proxima Centauri, from the Latin proximus, the nearest, and nearest it is. Of all the stars in the galaxy, this is the one closest to our Sun. Proxima is a red dwarf, an M-type star of the most extreme kind. Its mass is only about 5% of the Sun's. Its radius is roughly 1/7 of the Sun's, making it only slightly larger than the planet Jupiter. It burns so slowly and so faintly that in visible light, it emits just 0.5% of the Sun's brightness. Our Sun is 20,000 times brighter. Despite being our cosmic next-door neighbor, Proxima Centauri is completely invisible to the naked eye. It orbits the central pair at an almost incomprehensible distance, roughly 13,000 astronomical units. Light takes more than 2 months just to travel from A and B to Proxima. Its orbital period around the binary center of mass is estimated at around 550,000 years. One orbit, 500,000 years. For most of the 20th century, Proxima was treated as an astronomical footnote. The nearest star, yes, but a dim, unremarkable ember of little interest. That changed completely in 2016. In August 2016, a team of astronomers using the HARPS spectrograph at the European Southern Observatory in Chile announced a discovery that sent shockwaves through the scientific community. Proxima Centauri had a planet. The planet, designated Proxima Centauri b, was found using a technique called the radial velocity method, or Doppler spectroscopy. The logic is elegant. When a planet orbits a star, the star doesn't stay still. Both objects orbit their shared center of mass. The star wobbles slightly, almost imperceptibly but measurably. As the star rocks toward us, its light is compressed into shorter wavelengths, a blue shift. As it rocks away, the light stretches into longer wavelengths, a redshift. A precise spectrograph can detect these shifts and extract the planet's properties from the rhythm of the signal. What HARPS found was extraordinary. The wobble in Proxima's light revealed a planet completing one orbit every 11 days. Its minimum mass, approximately 117 times that of Earth. A rocky, terrestrial world, not a gas giant, not an ice planet, something genuinely Earth-like in scale. And its orbital distance, just 75 million kilometers from its star. For context, Mercury orbits our Sun at 58 million kilometers. Proxima b orbits 8 times closer to its star than Mercury does to ours. In any normal star system, that would make it a scorched inferno. But Proxima Centauri is not a normal star. It is faint and cool, emitting only a fraction of the Sun's energy. The habitable zone, the orbital band where liquid water could exist on a planet's surface, is not far from the star. It is pressed up tight against it, and Proxima b sits squarely within that zone, receiving about 70% of the energy Earth receives from the Sun. On paper, the conditions are almost perfect. An Earth-sized world, in the habitable zone, of the nearest star to our Sun, the closest potentially habitable planet ever found. The scientific community was electrified. The public imagination was captured. Headlines around the world declared that humanity's nearest neighbor might harbor life. But the paper version of habitability is a simplification, a dangerous one, because Proxima b orbits so close to its star, it almost certainly does not rotate freely. The same gravitational forces that keep our moon always facing Earth, tidal locking, would have seized Proxima b within a geologically short time after its formation, perhaps within a few 100,000 years. What this means is stark. One side of the planet faces the star forever. The other faces away into permanent night. Picture the planet. On one side, the day hemisphere, the star hangs motionless in the sky. Not the bright yellow disk of our sun, but a large, blood-red ember, ancient and smoldering, fixed in the zenith for billions of years. This is the substellar point, the eternal eye. Temperatures here, without an atmosphere to redistribute heat, could be hot enough to melt rock. On the other side, the night hemisphere, there is no star. There has never been a star. The surface has been plunged into darkness for the entire history of the planet. Temperatures plunge toward the cold of deep space, potentially hundreds of degrees below zero. The atmosphere itself, if there ever was one, would freeze and collapse here, its gases dropping out of the sky like snow. Between these two extremes lies a third region, the terminator zone, a narrow ring where the star sits permanently on the horizon, neither rising nor setting, casting an eternal twilight across the landscape. Temperatures here are intermediate, not scorching, not frozen. If liquid water exists anywhere on this world, if life has found any foothold at all, it would be here, in this ring of perpetual dusk, caught between a world of fire and a world of ice. But tidal locking is not the greatest threat to Proxima b. The real danger comes from the star itself. Red dwarfs like Proxima Centauri are not the quiet, stable suns we imagine when we think of a star. They are magnetically violent. Their interiors are fully convective, plasma churning from core to surface, generating tangled, powerful magnetic fields that periodically snap and release in catastrophic explosions called flares. Proxima Centauri is one of the most active stars known. It experiences minor flares almost constantly. But it also produces superflares, events of an almost incomprehensible violence. In 2019, a single flare caused the star's brightness in ultraviolet wavelengths to increase by a factor of 14,000 in just 7 seconds. A 2017 event made it 1,000 times brighter in radio wavelengths within 10 seconds. Now remember the planet. Proxima b orbits at just 7.5 million kilometers, 23 times closer to its star than Earth is to the Sun. When one of these superflares detonates, the planet receives the full impact. The radiation dose, X-rays, extreme ultraviolet, is estimated to be hundreds or even thousands of times more intense than what Earth experiences during a major solar flare. This radiation is ionizing. It tears electrons from atoms. It shreds organic molecules. It destroys DNA. Whatever chemistry might have once begun in the oceans of Proxima b, whatever fragile, complex molecules might have assembled themselves in some warm coastal pool, the flares would have dismantled them. But the most permanent damage is not to life. It is to the atmosphere. Each major flare releases a coronal mass ejection, a vast cloud of superheated plasma, hurled outward at millions of kilometers per hour. These clouds crash into the planet's atmosphere like cosmic shock waves, physically stripping gas away and hurling it into space. Even between flares, the stellar wind blowing off Proxima is thousands of times denser than the solar wind Earth experiences. A planet can defend against this assault with a strong magnetic field, the same shield that protects Earth. Generating a magnetic field requires a fast-rotating planetary core, and Proxima b, tidally locked, rotates once every 2 days. That slow spin is almost certainly fatal to a magnetic dynamo. Without a magnetic shield, Proxima b's atmosphere has spent nearly 5 billion years being systematically stripped away, layer by layer, by the very star it orbits. The habitable zone, in the end, is a trap. The same proximity that allows liquid water also ensures destruction. The most likely reality of Proxima Centauri b is not a blue, ocean-bearing world. It is a scorched, airless rock, its day side blasted by radiation, its night side frozen in billion-year darkness, its oceans long since broken apart and blown into space. The nearest world is probably dead. So, a dead world across an impossible distance. The question becomes, how impossible exactly? Every spacecraft humanity has ever launched has been powered by the same fundamental technology, the chemical rocket. Fuel burns, gas expands, gas expels backward, ship moves forward. Newton's third law, harnessed and refined over a century of engineering. The mathematics of this technology were laid out in the early 20th century by Russian pioneer Konstantin Tsiolkovsky. His rocket equation is elegant and brutal. The speed a rocket can reach depends on two things: how fast it can expel its exhaust, and the ratio of its initial mass, full of fuel, to its final mass, empty. The relationship between these is logarithmic, meaning that to go twice as fast, you don't need twice as much fuel. You need exponentially more. The most powerful chemical propellants humans have developed, liquid hydrogen and liquid oxygen, achieve exhaust velocities of about 4-5 kilometers per second. Impressive by any earthly standard, completely inadequate for interstellar space. To reach Alpha Centauri in 75,000 years using chemical propulsion, you'd need a ship where 99.9% of its launch mass is fuel. To make the journey in a mere 7,000 years, the required fuel mass becomes larger than anything in the solar system. To shorten the trip to a human timescale, say, a few hundred years, the equations break down entirely. You would need to convert the mass of entire planets into fuel. Chemical rockets are magnificent machines for reaching orbit, for going to the moon, for sending probes to the outer planets. But they are fundamentally interplanetary technology. The gap between the scale of interplanetary travel and interstellar travel is not a step. It is a cliff. If you cannot make the rocket fast enough, you can reframe the problem. Accept the slow speed. Accept the time. Build a ship that is not a vehicle but a world. The generation ship concept is as simple as it is haunting. Launch a crew. They will not reach the destination. Their children won't. Their grandchildren won't. Their great-grandchildren won't. The ship becomes a civilization unto itself. Generations are born into the metal corridors, live their entire lives between the stars, and die without ever seeing either sun, the one they came from or the one they are approaching. After perhaps 3,000 generations, some distant descendants of the original crew would one day see Alpha Centauri brighten in the viewport. The engineering challenges are monumental. The ship must be a perfect closed ecosystem, recycling every molecule of water, every atom of oxygen, every nutrient flawlessly for 70,000 years. A single failure of the life support system in year 40,000 would mean extinction for everyone aboard. Nuclear reactors would need to run autonomously for a period thousands of times longer than any reactor ever built on Earth. Radiation shielding of several meters of dense material, water, rock, would be required to protect the crew from the constant bombardment of galactic cosmic rays, adding colossal mass to the ship and making the initial launch even more demanding. But the engineering problems, enormous as they are, may be more tractable than the human ones. What does it do to a person to be born knowing they will never see a natural sky? To live their entire life in a metal cylinder, knowing the universe outside is lethal, knowing their only purpose is to sustain a mission that began centuries before their birth and will end centuries after their death. Psychologically, the pressure of such a confinement could be catastrophic. Sociologically, there is no human institution, no religion, no government, no culture that has maintained coherent purpose across 70,000 years. Languages change beyond recognition in 1,000 years. Civilizations collapse and are forgotten in 3,000. The mission's original meaning could be lost, corrupted, or inverted long before the ship arrives. A generation ship might reach Alpha Centauri not as an exploration mission, but as a floating ruin, or a society that has forgotten it was ever meant to go anywhere. The generation ship accepts the time. The nuclear era offered a different answer: attack the time directly. Between 1958 and 1965, One of the most audacious engineering projects in American history explored a deceptively simple idea. What if a spaceship could be propelled not by burning fuel, but by detonating nuclear bombs? Project Orion proposed exactly this. The spacecraft would carry thousands of small nuclear pulse units in its magazine. One by one, they would be ejected behind the ship and detonated. The ship's rear would be a massive armored plate, the pusher plate, connected to the cruise section by enormous shock absorbers. Each explosion would hammer the plate, and the shock absorbers would smooth the impulse into a steady, survivable acceleration. The physics were sound. Scale models were tested using chemical explosives and flew beautifully. The performance would have been extraordinary. An Orion vessel, accelerating over months of continuous nuclear detonations, could theoretically achieve 5 to 10% of the speed of light. At that velocity, a journey to Alpha Centauri would take not 75,000 years, but 80 to 130 years. A multi-generational mission, yes, but one measurable on a human timescale. Orion died not from engineering failure but from politics. The 1963 Partial Test Ban Treaty prohibited nuclear explosions in space. The project was canceled. The most powerful propulsion concept ever seriously developed was shelved before a single full-scale prototype was built. In the 1970s, the British Interplanetary Society took up the challenge with a purely theoretical study. Could a fusion-powered spacecraft reach the stars within a human lifetime? The result was Project Daedalus, an unmanned probe designed to reach Barnard's star in 50 years. Its engine would fire pellets of deuterium and helium-3 into a magnetic reaction chamber 50 times per second. Each pellet would be compressed by electron beams into thermonuclear ignition, a tiny hydrogen bomb, contained and directed by magnetic fields into thrust. The ship would weigh 54,000 tons at launch. 50,000 of those tons would be fuel. The payload, the actual science probe, would be 450 tons. After nearly 4 years of acceleration, Daedalus would reach 12% of the speed of light and arrive at its target in about 36 years. The numbers worked. The physics was sound. But two obstacles made Daedalus remain theoretical. First, controlled fusion ignition of this kind has never been achieved in any laboratory on Earth, let alone in a spacecraft engine. Second, the fuel. Helium-3 is extraordinarily rare on Earth. The study concluded that the only practical source of the tens of thousands of tons required would be robotic mining factories in the atmosphere of Jupiter. Both Orion and Daedalus proved the same thing. Nuclear propulsion can collapse the 70,000-year journey to a century. But it does so by demanding feats of engineering so vast cities riding nuclear bombs, fuel mined from gas giants, that they remain, for now, beyond our reach. What if the engine never had to leave Earth? Light exerts pressure. Not much. The sunlight falling on your hand right now pushes you backward with a force you will never feel. But in the vacuum of space, with no friction, that pressure accumulates. Given enough time and a large enough sail, the push of light can accelerate a spacecraft to impressive speeds. Solar sails are real. Japan's IKAROS mission deployed a 14-meter sail in 2010 and navigated to Venus on sunlight alone. But for interstellar distances, solar sails have a fatal flaw. The sun's light obeys the inverse square law. At the distance of Jupiter, it is 4% as strong as at Earth's orbit. At Pluto's distance, nearly negligible. A solar sail would gain speed beautifully within the inner solar system, then coast at interstellar speeds that would still require tens of thousands of years to cross the gap. The insight that transforms this idea is radical. What if, instead of the diffuse light of the sun, the sail were pushed by a focused laser, ground-based, enormously powerful, aimed precisely at the departing craft? In 2016, the same year Proxima B was announced, a consortium of scientists and philanthropists including Stephen Hawking and Yuri Milner unveiled an initiative called Breakthrough Starshot. Its goal: send the first human-made object to another star system within a generation. The concept dissolves the idea of a traditional spacecraft. Instead of a ship carrying fuel and engines, Starshot proposes a chip, a wafer of silicon no larger than a postage stamp, weighing a few grams. Into this chip, nanoscale engineering would pack a camera, a laser communication system, navigation sensors, and a power source. This nanocraft would be attached to a sail just a few meters across, thousands of atoms thick, made of a material reflecting light with near-perfect efficiency. The engine that accelerates this sail would not be aboard the ship. It would be on the ground. A phased array of lasers, hundreds of them, combined into a coherent beam, aimed at the sail from a high-altitude desert site. The total power, up to 100 gigawatts, more than the combined output of all nuclear power plants in a large nation. The acceleration would be savage. The nanocraft would be pushed to tens of g-forces, impossible for a human, irrelevant for a silicon chip. In 10 minutes of laser illumination, the sail would reach its cruising velocity, 20% of the speed of light, 60,000 kilometers per second. At that speed, the journey to Alpha Centauri would take approximately 21 years. 21 years. A mission launched when a scientist is 30 years old could return data before that scientist retires. The technological barriers are formidable. A 100-gigawatt laser array, sail materials with near-perfect reflectivity at atomic thickness, an entire spacecraft compressed into a gram of matter. But none of these challenges appear to violate physical law. They are engineering problems, not physics problems. That distinction matters enormously. But Starshot, in its current conception, reveals a profound asymmetry in the physics of interstellar travel. It is far easier to accelerate than to stop. A spacecraft traveling at 20% of the speed of light carries kinetic energy of staggering magnitude. It has no brakes. It carries no fuel. The laser that pushed it is 4 light-years away and cannot help it decelerate. So Starshot, as conceived, is a flyby mission. The nanocraft would streak through the Alpha Centauri system in a matter of hours, capture whatever data it can in those frantic moments, and continue into deep space forever. Engineers have imagined solutions. Could the sail be turned around to catch light from Alpha Centauri's stars and use it as a brake? The math shows the deceleration would take centuries. The ship would overshoot the system by light years before slowing meaningfully. Could a magnetic sail deploy against the stellar wind? Yes, but it would need to be kilometers wide and weigh many tons, destroying the fundamental premise of a gram-scale craft. Could a second laser array be prepositioned at Alpha Centauri to break the incoming ship? Yes, if you first sent a slower mission, arriving in 70,000 years to build it. Any mission that truly wants to stop at Alpha Centauri must carry its own deceleration fuel. And that fuel must be enough to shed exactly as much velocity as was gained during acceleration. In practice, this means a ship like Daedalus but doubled. One engine to accelerate, one to brake. The mass, the complexity, and the cost scale accordingly. The conclusion is stark. The technologies that make acceleration possible make deceleration nearly impossible. The technologies that make deceleration possible make the mission almost inconceivably large. The first generation of interstellar probes will almost certainly be flybys, a glimpse, not a visit. Even if the engineering problems of propulsion were solved, even if we could accelerate a probe to 20% of the speed of light and somehow bring it to a stop, there remains the simple question of survival. Space between the stars is not empty. It only appears so. The interstellar medium contains roughly 1 atom of hydrogen per cubic centimeter, an almost perfect vacuum by any laboratory standard. But it also contains something more dangerous, dust, microscopic grains of silicate, ice, and carbon, scattered invisibly through the void. At orbital velocities, a grain of dust hitting a spacecraft is a minor annoyance, a small crater in a heat shield. But a ship traveling at 20% of the speed of light is not moving at orbital velocities. It is moving at 60,000 kilometers per second. At that speed, the kinetic energy equation transforms every particle into a weapon. A grain of dust weighing 1 milligram, 1/1000th of a gram, traveling at 20% of the speed of light, carries approximately 1.8 gigajoules of kinetic energy. To put that in terms of something tangible, it is the equivalent of 400 kilograms of TNT, not a chip in the paint, an explosion that would vaporize the entire nanocraft instantly in a burst of plasma. Even particles far smaller than a milligram would punch through the delicate electronics of a chip-sized spacecraft with the force of a rifle bullet. And at these velocities, individual hydrogen atoms become a radiation hazard. The ship is essentially flying into a particle accelerator beam, with billions of hydrogen nuclei striking its forward face every second, slowly sputtering away the surface material and generating secondary X-rays and gamma rays that corrupt electronics and damage any sensors. Any interstellar spacecraft must be shielded. For large vessels like Daedalus, the solution was a 50-ton beryllium disk placed half a kilometer ahead of the main hull, a sacrificial shield that would be slowly eroded by impacts over the 36-year journey, absorbing the punishment so the ship behind it could survive. For a gram-scale nanocraft, there is no room for 50 tons of beryllium. Engineers have proposed needle-shaped geometries to minimize the forward cross-section, self-healing sail materials that vaporize at the surface and protect the chip behind them, and even using the propelling laser to sweep the path clear before the ship arrives. Each solution introduces its own complexity and mass. The deeper truth is this: the universe actively resists fast motion. The faster you travel, the more dangerous the apparent emptiness becomes. The darkness between stars is not a passive void. It is a minefield. Beyond the dust, there is a subtler and more pervasive threat. The interstellar medium is permeated by galactic cosmic rays, atomic nuclei, mostly hydrogen and helium, stripped of their electrons and accelerated to near light speed by distant supernova shockwaves. They stream through the galaxy in all directions continuously at nearly the speed of light. On Earth, we are shielded by two layers of protection: the planet's magnetic field, which deflects most charged particles before they reach the atmosphere, and the atmosphere itself, equivalent to several meters of water in radiation shielding effectiveness. Together, these layers reduce the cosmic ray flux at the surface to levels that living organisms can tolerate over a lifetime. A spacecraft in interstellar space has neither protection. The cosmic ray flux is constant and unrelenting. For a human crew on a generation ship or even a 36-year fusion mission, the accumulated radiation dose would not simply elevate cancer risk, it would make cancer statistically certain. Worse, cosmic rays affect the central nervous system. Studies of astronauts on the International Space Station, still largely protected by Earth's magnetic field, already show measurable cognitive changes after months of exposure. On a years-long interstellar journey, in the full fury of the galactic cosmic ray background, neurological damage would accumulate continuously. Memory, problem-solving, judgment. The crew's ability to operate the ship could degrade over the course of the mission. For the silicon brain of a robotic probe, the threat is different but equally serious. A single high-energy cosmic ray particle passing through a microchip can flip a bit, change a 1 to a 0. In navigation software, this could send the probe off course. In the data store, it could corrupt irreplaceable scientific measurements. Over a 21-year journey, the cumulative bit flip rate from cosmic rays could be catastrophic for unshielded electronics. The darkness of the interstellar void is not a metaphor. It is a radiation environment that erodes matter and mind alike. We have arrived at a conclusion that seems, on its face, like an argument for despair. The destination is almost certainly a dead world, an airless, radiation-scorched rock tidally locked to a violent star. The journey, with our best current technology, would take 75,000 years. The most optimistic, realistic proposal, Starshot, would deliver a glimpse in 21 years, but stopping requires technology we do not yet possess. The space between here and there is not empty. It is laced with dust that becomes TNT at relativistic speeds, and saturated with radiation that erodes both silicon and flesh. So why do we look? Why do scientists dedicate careers to studying this point of light? Why do billion-dollar initiatives take shape around it? Why did the announcement of Proxima b, a probably dead rock, generate headlines around the world? Because Alpha Centauri is a mirror. It is the closest thing we have to a cosmic measuring stick for our own limitations. By studying this system in detail, by understanding why Proxima b lost its atmosphere, why the habitable zone around a red dwarf is a radiation trap, why the physics of propulsion makes the distance functionally impassable, we understand ourselves. We understand the depth of our isolation. We understand how extraordinarily improbable our own circumstances are. A stable G-type star, a planet at just the right distance, a magnetic field, a moon that stabilized our axial tilt, an atmosphere that has persisted for billions of years. None of this was guaranteed. Proxima b shows us what happens when even one of these variables is wrong. Alpha Centauri is also a mirror for our ingenuity. Every impossible problem generates ideas. Orion gave us nuclear pulse propulsion concepts that could one day power not a starship, but a fast transit system through the outer solar system. Daedalus advanced fusion research. Starshot is pushing the frontiers of laser technology, materials science, and chip miniaturization. The dream of interstellar travel, even an unreachable dream, has repeatedly catalyzed real breakthroughs. The impossible problem of today generates the transformative technology of tomorrow. And finally, Alpha Centauri is a mirror for something harder to name, the irreducible human compulsion to look over the horizon. The same impulse that drove the first boats into open ocean. The same impulse that pointed a rocket at the moon. The same impulse that will, eventually, point something faster and smarter than Voyager toward the stars. We know the planet is probably dead. We look anyway. Because the act of looking, the discipline of trying to understand what is out there, even when it is unreachable, is itself what defines us as a technological species. 70,000 years of darkness. It is, we now understand, not just a measure of travel time. It is a description of every barrier that stands between us and the stars. The physics of propulsion, the violence of the interstellar medium, the hostility of red dwarf environments, the fragility of human biology over cosmic timescales. Alpha Centauri is 424 light-years away. In all the ways that matter to our civilization, it might as well be on the other side of the observable universe. The laws of physics have placed it just close enough to tantalize us and just far enough to humble us completely. Our sun, in contrast, is a miracle of stability, a calm, steady lamp in a galaxy full of violent fires. Our Earth, with its liquid water and thick atmosphere and protective magnetic field, is not typical. It is rare. The universe has not made it easy to build a planet like this, and it has made it effectively impossible to leave and find another one. There is a particular kind of peace that comes from accepting this, not the peace of giving up, but the peace of accurate understanding. The cosmos is vast. It is mostly empty. It operates on timescales that dwarf the history of our species. The stars are not stops on a road. They are islands in an ocean so wide that even light takes years to cross it. And yet here we are, measuring the wobble of a distant red star, calculating the thickness of a sail made of atoms, designing a laser powerful enough to push a postage stamp to the stars, imagining in careful, peer-reviewed detail what it would take to cross the void. The journey to Alpha Centauri is impossible for us now. It may be impossible for a long time, but the act of confronting that impossibility honestly, measuring it, mapping it, refusing to look away from it, is not a defeat. It is the beginning of wisdom about where we are, and perhaps, eventually, the first step towards somewhere else.